Welcome to the third episode of our webinar series, Exploring Nanomaterial Synthesis Using Liquid Phase Transmission Electron Microscopy. My name is Nienke Krantz, and I'm an application scientist working from the European region. This webinar series has a focus on the synthesis of nanomaterials. So we're really excited because this series coincides with the launch of our new Triton AX system. The brochure is actually here in the handouts, so you can download that if you're interested. But what makes Triton AX so unique is its wide in situ temperature range. It can go all the way from -50, yes, minus, so very cold, to 300 degrees Celsius, which opens up really exciting possibilities. We can now study materials that form in high boiling point solvents, and on the other extreme, we can use low temperatures to protect more sensitive materials from the electron beam. And that's a little bit what this talk today is all about, the electron beam. There are several very experienced speakers in this series using liquid phase TEM for these types of studies for many years. So be sure to sign up also for any of the other webinars following this one. There's a couple more coming up. You can sign up via our website. The links are up there. A couple of household items before we introduce this speaker who is here with me. So everyone is muted due to the audience size, but if you have any questions, please add them to the question box in the GoToWebinar panel. This way I can then read them out to our speaker at the end of the webinar, and then your questions can be answered. If there's too many questions to be answered, we can always email them to Andreas later, so he can answer via email. At the end, we will have a survey pop up, so we would really appreciate if you could take 1 minute to fill it out, please. So that is all the household items. We can actually start now. Let me introduce today's webinar presenter. We are really honored to have Dr. Andreas Hutzler here speak on the topic of quantifying processes in liquid phase electron microscopy. Andreas, a little bit of background on himself. Andreas Hutzler studied electrical engineering, a bachelor's in 2011 and a master's in 2014, focusing on semiconductor technology, photonics, and medical electronics at Friedrich Alexander Universität Erlangen-Nürnberg. During his doctorate, he developed new liquid cell architectures and applied those in the field of materials science to study growth and degradation mechanisms of nanostructures using liquid phase transmission electron microscopy. Since 2018, he works on the understanding and modeling beam damage in liquid phase TEM. And in 2021, he joined the HIERN as a team leader and head of TEM lab. During this time, his focus has been extended towards applying quantitative electrochemical liquid phase TEM for studying degradation mechanisms of energy materials utilized in electrocatalysis. So, Andreas, thank you so much for joining us. And if you're good, I am going to mute and also remove my camera. And then we can start the webinar whenever you're ready.
All right. Can you all see my screen and hear me?
It looks good.
Cool. Then let's start. Hi, everyone. Thanks for listening. Yeah, we are working since 2014 with liquid phase electron microscopy. And today I'd like to give you a few insights of what we are doing with liquid phase EM. Also in terms of quantitative analysis of processes that are observed with liquid phase EM. But before I go to the synthesis studies, I actually want to do the opposite. Look at degradation first, because this is what we are doing over the past few years. We look at degradation of electrocatalysts, specifically in PEM water electrolysis. And what you see here is an explosion view of such a PEM water electrolysis cell with at its heart two catalyst layers. We put water in. At the anode side, we have the oxygen evolution reaction. Oxygen comes out. And then we have a separator membrane, which is proton conducting. And this can then transport protons to the other catalyst layer where the hydrogen evolution reaction takes place. And then we get hydrogen out, what we would like to take to use for energy storage. how do we study these degradation processes? Usually we do this ex situ, so we compare ultramicrotomy cross sections from this catalyst coated membrane in tested state, so after electrochemical stress, and that's these 4 samples here, and compare it to a conditioned sample, so more or less begin of test sample. And if you use iridium, a metallic iridium here as a starting material, this has an FCC phase, and it has an only very thin oxide layer on top. And when we cycle, then we can see, okay, there's at least oxidation happening. What you can see here at the evolution of additional peaks, which is due to the iridium oxide having a different structure, namely rutile structure. And what you can do is look at the oxidation state, what we did here with 4D STEM. Problem is only that you only have a before and after state, and we don't know what is happening in between. And there, liquid phase EM comes into play, and our vision is to, at some point, being able to apply liquid phase TM in electrocatalysis to study such degradation phenomena during their occurring. So vision is to combine some kind of advanced liquid cell architectures with such an electrolysis cell. And of course, the electrolysis cell is much too large, so we focus rather on the catalyst layers. And hopefully at some point we will be able to put those into the liquid cell and study processes like this. What you see here is a carbon coated platinum electrode, and on top there are some silver structures. And silver is here used as an electrocatalyst for CO2 reduction in a potassium bicarbonate solution. And when we apply a reductive potential, then nanostructures dissolve at a certain place, and at another place there are some dendrites growing. What I have to say here is we have a reductive potential, so there's no oxidation happening here, but still we observe dissolution. When we switch off the potential, then these dendrites that are freshly grown dissolve again. And this is because of our electron beam. So our electron beam obviously does something with a sample solution, which we need to understand before we can study degradation processes. So the question would be, can we apply operando liquid phase EM in a quantitative way? Back then in 2018, so this was a very first publication from our team in 2018, and there we finally come to the topic nanomaterial synthesis, where we studied silver shell growth on gold nanorods. And what you see here in this video is a gold nanorod, and upon electron irradiation we grow this shell around it. And you see another particle above here, which is dissolving when you look closely. And this is silver bromide, stemming from the fact that we stabilized our gold nanorods with ceriammonium bromide, and we irradiate a silver nitrate solution. And if you put silver ions and bromide ions together in a solution, this will precipitate as silver bromide crystals, because this has a very low solubility. We can then see that we really have a silver shell grown around these nanorods, and can already postulate a mechanism from this video, namely that so we have a small amount of silver ions in the solution, which we take out due to electron irradiation. So we reduce them. They will deposit around or on top of the pre-existing gold crystal by means of an underpotential deposition. And by taking out the silver ions from the solution, we disrupt the solution equilibrium between silver bromide and its ion pair. And then what is happening is that silver bromide crystals, like this one above here, dissolve. And the cool thing about that is they dissolve atomic row by atomic row, what you can see here in this edge-on video where you see individual lattice planes disappear. We can learn more about this underlying process. Namely, we can look at the dynamics, so we can see how the shell grows over time, and we can even see that the shell grows anisotropically, so it grows faster in transversal direction than in longitudinal direction. But everything is electron beam induced right now. And if we compare this to what is happening under light conditions without the electron beam, we start with the gold nanorods that are stabilized with ceriammonium bromide in this kind of reddish solution. And if we add a reducing agent, ascorbic acid, then we observe a blue shift of the solution, so that the solution turns greenish. And in the absorption spectra, we actually see two peaks. One of them is can be assigned to a silver absorption peak at roughly 400 nanometers. And the second one is the longitudinal surface plasmon resonance peak. And this is highly sensitive on the aspect ratio of these nanorods. So when the shell grows anisotropically, we will change the aspect ratio, and this causes a blue shift of this LSPR peak. When we prepare the solution in daylight, then we observe an increase of the silver peak or silver absorption peak, while when we switch off the light in the labs, we see a decrease of the silver absorption peak, but still a blue shift of the LSPR peak. And this is more or less the opposite of what we would expect from when looking at the liquid phase EM experiment, where at high electron dose rates, we see the silver shell growth. At low electron dose rates, we rather see a silver particle growth. And under light conditions, it's the opposite. And the reason for that is the influence of ionizing radiation. And you can nicely see what happens when ionizing radiation hits matter. Here we have this gaseous atmosphere at roughly 100 kilometers height. And we can already see that there is an effect. We have an excitation of molecules to radiate. And we have a very similar process in liquid phase EM. We call this process radiolysis, and that was already described by Marie Curie as an electrolysis without electrodes. And this will surely influence our observation. We can observe or induce growth of nanomaterials. We can also induce etching of nanomaterials just with electron irradiation of precursor solutions. And we also have a strong influence on the acid-base chemistry. I will show this in a second. So actually, we can reformulate the initial question to a new one. We can do quantitative analysis with it when we account for the influence of the electron beam. So we need to understand exactly what is happening here. How can we access electron beam effects? Well, the obvious thing is just imaging. We can see the dynamics of processes that we observe. We can also do in-beam measurements, like shown by Patricia Abelan, doing in situ yields, which can be used, for example, for quantifying the radiolysis products. We can also do out-of-beam measurements, like, for example, this electrochemical measurement. So we can do electrochemical sensing of certain species. And what we can always do is look at structures that haven't been irradiated during our in situ experiments and compare them to irradiated ones. So what is happening when ionizing radiation hits our solvent molecules? We mainly use water or aqueous systems. And when the electron beam hits the water, we get excitation, ionization. The water molecule is ripped into its pieces and will rearrange. And after some time, roughly 1 microsecond, these fragments of water will rearrange into what we call primary radiolysis products or primary species. And among them are really highly reactive species like the solvated electron, hydroxide radicals, hydrogen radicals, superoxide radicals, but also molecular ones like molecular hydrogen, molecular hydrogen peroxide, and as I said, H+ and OH-. When we know how much of these primary species we generate, the problem can be solved by a simple solution kinetic simulation. So we can simulate what is happening in the liquid cell chemically, but already for pure water, this ends up with 12 to 17 species, depending on the model that you use, coupled over 86 chemical reactions just for the pure water. So interpretation becomes a bit challenging, so to say. Luckily, my former postdoc, Birk Fritsch, he tried to tackle this problem and build up a Python code that is able to solve this partial differential equation, which basically has 3 terms. The first one, so this greenish term, accounts for the generation of the primary species via an energy transfer. So it basically contains all the material and beam parameters. And then we have 2 terms describing the chemical reactions, the reactants that are consumed and the products that are formed. The software just uses a text file containing all the chemical equations and their rate constants. And then a second text file contains the G values and initial concentrations. And then the software automatically generates a concentration matrix and is able to solve this partial differential equation. And what we end up with are these kind of plots, so concentration evolution over time. And this is a very typical plot. And what you can see in there is one transient regime at the early stages, and then at some point a steady state will form if we did everything correctly. So let's see what we can do with our radiolysis modeling. And therefore we look at also another experiment that we did in 2019. And back then we weren't able to simulate all the stuff. We just made this nice observation. We saw a gold platelet in a chloroauric acid solution, and this obviously dissolves when it's in contact with a gas phase, so with a gas bubble here. And what we postulated is that it cannot be that there's only hydrogen inside this gas bubble, because hydrogen is not able to etch gold, so there must be some chlorine containing species in there as well. And a second thing that we postulated is there must be some kind of gold mass transport via the gaseous phase, because when the particle is dissolved or the platelet is dissolved, more particles are growing beneath the gas bubble, and this looks like an isotropic growth. So it's not just happening there where the particle gets etched, but also at different places. And when we now look at the simulation outcome that we were only able to simulate 3 years after, we built up a very large reaction network containing 42 chemical species, coupled over 184 reactions containing all the chlorine species, the gold species, and also the water. And if you look at the steady state formation over the electron flux density, so how many electrons we put into the or we irradiate our solution with per area and time, we can directly see, so in this gray shaded area, we recorded this video. We can directly see that we have a high concentration of molecular HCl. And yes, the dissociation of HCl is taken into account. This happens with a rate of 10 to the 5 mole per second, whereas the generation of molecular HCl happens happens 5 orders of magnitude faster with a rate of 10 to the 10 mole per second. And the second thing we see down here is that we have also a gold dimer that is known to be volatile. So it can directly explain what we observe in a let's say, qualitative way. Now, what about pH in irradiated solutions? Obviously, we have to rethink the pH because we generate H plus and OH minus at the same time. So the concept of pH loses much of its meaning. And that's why we introduce a new measure that we call radiolytic acidity pi star. And that's the logarithmic ratio of the concentrations of H plus and OH minus. So basically, it tells us which of the species has a higher concentration upon irradiation. And in this plot, we have our initial pH at the y-axis, whereas we have the dose rate at the x-axis. And what we can see when we increase the dose rate, we always drive the system towards a more or less neutral condition, meaning that the concentrations of H plus and OH minus are more or less identical. However, if we look at the ion product, we also see, and that's because of our electron irradiation, we strongly increase the concentration of both species. But we always end up in this more or less neutral condition for pure water. When we now add some different chemical species like nitrate ions, we can also change this. So for the nitrate ions, we more or less have an alkaline condition over the entire dose rate range. Only at very high dose rate we have this turnover point to an acidic regime. Where this turnover point is located at largely depends on the concentration. So you can see here the 1 millimole case and the 10 millimole case. For the case of bromide ions, this is a bit different. So we start in an acidic regime, we have a turnover to an alkaline regime, and then at high dose rates, again, a turnover to acidic regimes. Surprisingly, the chloride ion does not change too much. So the greenish color data points are the case with 1 millimolar chlorine, and compared to pure water with the bluish data points, this doesn't change too much. So this is all simulation work now, and now we want to see whether we can also see this change in acidity in our in situ experiments, and therefore we would need such kind of indicator strips, but of course they are much too large for putting them into our liquid cells. So our colleague Thais Cournot had the idea, okay, we could use alpha iron oxyhydroxide named goethite as nano indicator strips. And she did very extensive ex situ characterization looking at the structural evolution, so growth or dissolution of these needle-like structures, and found out, okay, at acidic conditions, we have an etching of these needles, which proceeds faster in width than in length. And this process involves the release of iron 3+. Whereas at reductive conditions, we have a faster etching in length than in width under the release of iron 2+. And under alkaline conditions, she even observed growth. So we've put together a chemical network to simulate the conditions. And this is the outcome. What we see here in the green data points, we have the acidic case under the release of iron 3+, and we start in an acidic regime. We go down at higher electron flux densities to more or less neutral conditions. So the neutral condition is the dashed line here. Under reductive conditions, it's different. We start in an alkaline regime and go up to more neutral conditions as expected for the pure water case. And in both cases, we have a very high concentration of H+ and OH-. So we then did 2 experiments at 2 different electron flux densities, namely 21 and 167 electrons per square angstrom second. And this is the outcome. For the low electron flux density case, we have faster etching in width than in length, with a ratio of roughly 5:1. And when increasing the electron flux density, the etching proceeds faster. However, the ratio gets way smaller and the error bars even overlap, which nicely fits to the simulation of our acidic conditions. So at low electron flux densities, we have a more acidic regime, and when we increase, we go down to more neutral regimes. So also here, our simulation work seems to qualitatively work. Now, can we learn something else, or can we get quantitative insights? And this very experiment was already shown by Tyler in the last session, so I will keep it short. But what we did here is we also used the silver nitrate solution with an additive tertiary butanol. And this additive is an OH radical scavenger, which will prevent the dissolution of silver. You have to trust me for a moment. In a few slides, I will explain why this is happening. And what we wanted to do is we wanted to understand growth and nucleation, and we start with the growth. There we looked at the temporal evolution of the size of the nanostructures that we observed, and they did several experiments at different dose rates. And what they got is a plot like this with the data points in blue. And these are really statistically relevant data points because we have hundreds of particles characterized in there. So what we did is we did our kinetic modeling, and this is the outcome for the silver species, where we have kind of a transient regime, and then at a certain point we have a steady state formation. And when looking at the steady state and plotting it over the dose rate, we get this kind of plot and see that there's a power law dependency of the individual species on the dose rate, which was already introduced in 2014 by Nick Schneider and Francis Ross. And now we can do the following. We have this growth model, which is the LSW model. We have a concentration in there, and we have our concentration dependency on the dose rate. Here we can plug that equation into here and compare, so to say, the slope of the data points with the slope of our individual species. And we quickly found out, okay, it must be a diffusion limited growth. And the species that come into play, so which have the right slope here, are the silver minus and the silver 4 clusters. For the silver nucleation case, this was a bit more complicated. And what we did here is we looked at the number of particles over time for the 3 different dose rates. And first had the idea, okay, let's try the classical nucleation theory model. And it actually gave a good fit. However, when looking at the fit parameters that were used here, it turned out that this is a very unphysical result because we had critical radii of the order of below 1 nanometer. So basically the size of an, more or less one atom is already the critical radius, and also the solubility predicted by the model of elemental silver species was very high, and reduced silver species basically don't have any solubility, so they are mostly insoluble. So this model did not work. So we thought about, okay, maybe it's a non-classical nucleation that we see here, and we thought about, okay, let's try this cluster aggregation model. But here we had another problem, namely that none of the species that we simulated had were showing a negative slope over the dose rate, what we got from here. So this steady state did not work out. And we then thought about, okay, maybe it's a transient process, maybe it already happens in the early state of this steady state formation. So what we did, we looked at each point here in time and plotted this over the dose rate, and what we got was this kind of plot. So this is the exponent, what we got from the power law, plotted against time. And only for one species, it turned out that this crosses our experimental data region, here shown in violet, which is the silver 4-2+ cluster. So we think that the nucleation of silver happens here with a cluster-cluster aggregation involving this silver 4-2+ cluster, and also a sanity check. So when thinking about the concentration of these species in the solution and their diffusivities, ends up in a collision time of roughly 1 millisecond. So this seems to work, and now we can even learn something new from our radiolysis modeling. But can we also tune it? So can we somehow influence that when tuning our electron beam parameters, or having a liquid flow through the liquid cell or so? And actually the silver system is quite nice for studying this phenomenon, because reduction is happening via primary radiolysis products, so the solvated electron or hydrogen radical. As reducing agents, they form reduced silver, and these reduced silver atoms can then cluster to larger silver 2 or silver 4 clusters. Whereas the oxidation, this does not happen with primary radiolysis products, but with a secondary radiolysis product, which is molecular oxygen. And molecular oxygen has to first build up in a primary reaction with the hydroxide radical and the superoxide radical. And this is actually also the reason why this OH radical scavenger prevents etching of silver. So we can now try to study the question, can we actually flush away our radiolysis products? Because we can nicely separate reduction and oxidation due to this reaction with primary and secondary radiolysis products. So we went back to the famous Greek saying, Panta rei, everything flows, which goes back to Heraclitus of Ephesus and means on those who step into the same rivers, different and different waters flow. Translated into our world, this means when we follow a water molecule going down that little creek here, we see it once and then it's gone. And actually, the group at Nanogune in Spain have simulated a condition which influence a flow on the radiolysis product would have. And it turned out that molecular species like molecular hydrogen or oxygen can be effectively flushed out which makes sense because they are stable. Whereas in the case of the very reactive species like hydrogen radicals or solvated electrons, this is not that easy because they will basically react with everything they encounter. And it turned out that if you flush away these stable products, you can even have a more reactive environment by a process called self-scavenging, which is prevented by flushing out the secondary radiolysis products. So we tried to study this phenomenon, and therefore we applied a certain flow rate of 0.33 meters per second and had a certain dwell time in STEM mode. And what we observed here is this beautiful silver platelet growth. So it was again this silver nitrate solution. And when we reduced the flow rate to very low flow rates and increased the dwell time, we basically observed nothing. So what we did is we manually put in silver there by a chronopotentiometry. So we applied a reductive potential and grew silver electrochemically. And what happened then is the silver structures immediately dissolved after putting them in. So we can obviously switch from a reductive regime to an oxidative regime. And my PhD student, Andreas investigated this in very much detail. He always recorded a video under certain flow and beam conditions, and then one of the parameters was switched, and this is the result what we got. So more than 20 data points. We have the dependency of dwell time and flow velocity, and we obviously have two different regimes, namely a growth regime and an etching regime. So the green data points indicate growth, and the pink one indicate etching. And the darker they are, the faster is the process. So we have the fastest growth down here and the fastest etching up here. When we now compare this to our simulation output, and what we did here is we modified our model slightly with a convection term by providing fresh liquid or fresh precursor. And when we now look at this one species that we identified of being responsible for the growth of silver 4 clusters, we can see that we have a very low concentration in that region up here and here, whereas in the low dwell time and high flow velocity regime, also at low flow velocities, we have a very high concentration of these species, which would already indicate growth. Let's look at it in a bit more detail and specifically at the dwell time effect. So when going up with the dwell time in this graph, we actually have our transient period intersected with our dwell time, because the dwell time is much smaller than the transient period, so before a steady state is forming. So to say, we interrupt the process during the transient phase, and what we can see is that certain species still decay. They have a very high concentration in the beginning and they decay in concentration, whereas the oxygen, it's a very slow process. It takes some time for the oxygen to build up and reach sufficient concentrations. Then looking at the flow. Here we had a flow of roughly 0.1 meters per second. And when changing the dwell time, we see at very low dwell times, we have a high growth velocity or growth rate, and then the growth rate drops. And at some point, we even observe etching when passing this line. When looking at the concentrations of the individual silver species, which are responsible for the growth, it turns out, okay, they are also losing in concentration, whereas the oxygen that starts at a very low concentration and builds up for higher dwell times. And here for the silver case, as I indicated before, silver is mostly insoluble, so we can even estimate an expected volume that we grow. And surprisingly, this even fits in a quantitative way. When looking at these 200 nanoseconds, we end up with almost the same amount that we measured with our in situ electron microscopy. One more thing to mention here is if we have the control over our beam parameters and also flow parameters, we can even tune we can even tune the growth and dissolution to what we call a net neutral regime. To a state where we don't have any growth or dissolution induced by electron irradiation. And this would be an interesting point to do electrochemical experiments, because there we don't expect any interference, at least not in terms of growth and etching of the electron beam. Can we also simulate this spatially resolved? And therefore, we also teamed up with CIC Nanogune, Stefan Merkens, Giuseppe De Salvo, and Andrei Chubelin. Giuseppe is now at CNRS in France, but this study was still done together last year. And here we had the idea, okay, let's plug our Python code for radiolysis simulation in their spatially dependent finite element simulation in COMSOL. What we had to do here is strongly reduce the amount of chemical equations that are involved, because otherwise the simulation of a single pixel and then also the whole volume would take ages. But what you can then do with this very comprehensive 3D model is to simulate stem, diffusion, and flow all at once. And we did this for the case of water, just for reproducing the 0D simulation that was provided by Nick Schneider in 2014, which translates to the case of more or less graphene liquid cells, where you irradiate the whole liquid volume at once. And then when looking at certain different cases, so a larger volume of liquid and you just irradiate a tiny amount of that in a closed configuration or open configuration or even under flow conditions, it turned out that for a first rough approximation, you can even apply a 0D model and you hit, let's say, the result within one order of magnitude. Whereas if you want to simulate spatially dependent phenomena, so for example, if the electron beam is much smaller than your liquid volume, then you might need a more sophisticated 3D model, which we provide here in this publication. Enough to radiolysis. There are also other beam effects that we studied a few years ago. One of them is the question about, does the electron beam increase our temperature in the solution? And there we used a method, so an in-beam method that we call parallel beam electron diffraction, which utilizes the lattice expansion that you get from if you heat up a crystal, ending up in the contraction of the diffraction rings. And you actually have to be very precise for this, for getting some results. So 1 degree C equals to roughly 15 ppm of a single pixel. And this is the change that you get from heating the sample up from 20 degrees C to 900 degrees C. You need a special microscope alignment for it, and also take care about charging effects to be that precise. but it was possible to do this measurement in situ. What we had to do is we had to introduce a gas bubble, because with a micrometer thick liquid, you basically lose the zero beam. But with a gas bubble, we did some measurements with roughly 140 nanometers of liquid, so 70 above the bubble and 70 nanometers below the bubble. And what we did is we applied a temperature stimulus starting at 30 degrees C, heating up to roughly 70 degrees C. And we see that our data points, which are the parallel beam electron diffraction measurements, nicely follow the temperature curve of the heater. We get a slight overshoot, which is kind of expected. And then at some point we switched off the heating and the temperature went down to a certain point, but not to room temperature again. And here we're curious about the dependency on the dose rate. And what we saw is when we increase the electron flux density, then we can also increase the seating effect. And it turned out that when you have a gas bubble and when you have some nanostructures that you use for diffraction, you can actually heat up the sample quite a lot. So there is a significant beam-induced heating in case you have this gas bubble. I think in case you don't have this gas bubble, the heating will be much less, because the heat transport is much better in the water. Yeah, so take-home message: seeing is believing, but feeling is the truth. I hope I could show you that our approach with testing combined with radiolysis modeling to map the influence of the electron beam is an effective strategy that can be utilized to use the electron beam for nanomaterial synthesis, for example. We can also use this approach to mitigate electron beam effects. What we should do in each case is doing reference experiments, so see if under real world conditions we observe the same phenomena. And all what I've shown is published in this recent review that we published together with Saren Lee, Nick Schneider, and Francis Ross. And maybe for some of you, this might be of help when doing radiolysis simulations. With this, I'd like to thank you for your attention. Of course, a huge thanks to my team and all the collaborators that are listed here. And before I stop, I'd like to make a little advertisement. I'm organizing together with Jen Cookman this Gordon research seminar on liquid phase electron microscopy, and I would be happy to see some of you there. And with this, I'd like to thank you for your attention.
Thank you so much, Andreas. That was a really great presentation. And I think not only does it show that you need to do your research very well when doing liquid cell microscopy, but also all the effects that can happen and that you need to keep in mind when you do liquid cell microscopy for any studies that you're doing, being it heating or electrochemistry or anything at all. So great presentation. Thank you for that. The floor is open for questions. Please type your questions in the question box. There are already a couple of questions that have come in, so I'm just going to read them to you if you are ready.
Yeah, sure.
Good. Well, the first question that came in was, how do you obtain sufficient signal to noise ratio in eels for quantitative estimation of radiolysis-induced transient molecules?
Yeah, good question. So these experiments that I've shown were conducted by Patricia Avelan at CNRS. They were looking at thin ice films, and they really have to be extremely thin to get a sufficient signal to noise ratio. And even in ice, as far as I remember, there were diffusion effects observed. but yeah, sure. So in a liquid cell with micrometer thick liquid layers, you probably don't get any sufficient signal from eels. Yeah, when I showed these parallel beam electron diffraction measurements, there we had a very similar problem, maybe not as severe, but for roughly a micrometer thick liquid layer, you even lose the zero beam, so you don't need to use a beam stopper anymore to do diffraction, actually.
Yeah, that is a really good point. Yeah.
Yeah.
Maybe I was wondering then on top of that as well. So if you want to do eels, usually what people do is they thin the liquid layer out, for instance, with gas formation, but you just showed the temperature changes that can undergo that as well. So would you say that maybe if you want to do something like that, form a gas bubble, maybe do some analysis on your sample, that is basically maybe the end of your sample, or would you say you can flow back gas, flow back liquid in and then continue? How would you? What do you think of that?
I think it strongly depends on the liquid you're using, how sensitive it is to radiation. It could be a way to introduce gas bubbles to thin the liquid layer down for doing eels. I mean, you might get additional heating effects or other effects that we don't know about. You could also, I mean, everything is not optimal right now. You could also go to graphene liquid cells or very thin liquid layers, but those have the same issues in principle. Yeah.
Clear. Thank you. Okay, next question is, thank you for the great and insightful presentation. For the simulation of radiation chemistry under beam irradiated conditions, given that a significant amount of electron beam would be transmitted in the TEM system, what fraction of the electron beam did you assume to be transmitted versus absorbed into water on your calculation? And does this absorption vary with water thickness? And do you have experimental support for these assumptions?
So in our experiment, I would not expect a single electron to get stuck in the liquid. So I guess every electron is being transmitted, maybe apart from those who are somehow scattered elastically towards the liquid cell encapsulation or so. So these solvated electrons that we are considering, they are not primary electrons. They are, so to say, fragments of the water molecules. Yeah, so the energy of the primary beam, or the energy of primary electrons, is transmitted or is transferred via inelastic scattering. So the primary electrons lose some of their energy, transfer their energy to the liquid, and this excites the water molecules or ionizes the water molecules to induce this radiolysis. So what we typically do is we account for certain dose rates, and dose rates, I even have a slide for it. So that's a dose rate is the amount of absorbed power by the specimen, whereas the electron flux density, that's the parameter that can be controlled via the microscope interface. Right, so if you tune your beam parameters, although it's mostly written by means of dose rate, but if you look at the unit, it's in electrons per square angstrom second, or per area and time. And if you want to translate this into a dose rate, so the energy that is absorbed, you need certain material parameter like the stopping power, the mean free path length, which is actually dependent on the not only on the liquid but also on the acceleration voltage. So if you go down with the acceleration voltage, the mean free path gets also shorter. That's also why in an SEM processes are much more severe than in TEM. If you want to do if you want to study processes without too much influence of an electron beam, I would suggest you go up with your acceleration voltage as much as possible. So, for example, 300 kV or so. Yeah. So it's basically in elastic scattering and energy transfer that induces all these chemical phenomena.
Would you then also have, or would you say that maybe either TEM or STEM would be, let's say, better for liquid cell studies? What would you choose normally if you would need to make a choice between the two?
So parallel beam versus STEM, you mean?
Yeah. Yeah.
Also good question. Yeah, there's no simple answer for that. It's highly dependent on the material system that you study. I mean, STEM has certainly a better mass thickness contrast. If you want to study heavy materials, you get better signal to noise ratios with it. You saw that when you tune the dwell time, you can already induce some phenomena or suppress something that you can then also compensate with a flow. So there's not really a simple solution for that. I mean, one thing maybe also to consider is when using STEM, you get the best resolution for structures that are at the top membrane. And for TEM, you get the best resolution for structures located at the bottom membrane, right? These are all things that you might want to consider. In terms of radiolysis, it's a very difficult question. It's highly dependent on the chemical system that you use.
That's very clear. Okay, thank you. Let me see, I'm going to grab a couple more. There's a couple of questions about the temperature studies that you've done as well. I think these were slides 29 and 20 and 30, or maybe at least 29. So in 29, the question was, what microscope alignment exactly is involved for temperature measurement?
Yeah, so what we used here was a Titan Cube Themis with a three condenser lens system. And this enables that you adjust the ratio C2 to C3 ratio and adjust the beam vergence. You need a very highly parallel electron beam, because consider if you have a convergent beam, already a change in height would cause a change of the ring radii. And this is what we want to prevent. When we have a very high, highly parallel electron beam, then also a change in height does not make any change in the diffraction ring radii. And that's what I meant with advanced microscope alignment. It turns out that the factory alignment is not enough for these kinds of measurements. However, if you can exclude a movement in Z direction, you can actually also use a two condenser stage system, which we tried out with a Talos F200i. And you can get a certain resolution. You have to make some previous assumptions, like you don't have or you don't expect any movement in Z direction, which is a bit difficult. If you heat the sample up, it might expand to some extent, right? But if you just study temperature at room temperature, you can say, okay, there will be no bulging apart from the bulging that you induce by your liquid pressure or inlet pressure. So you can say, okay, maybe I don't care, and then you can still do temperature-related measurements. But still, so we have this ultra microscopy paper mentioned here, and there everything is described. So there's also a specific evaluation algorithm that fits the the aberrations, the residual aberrations from the diffraction rings. And therefore we get a very sharp diffraction peaks or very sharp diffraction peaks in the profile.
So while you are doing these measurements, do you see then any drift as well? Because the temperature change is so big, I would expect that if there is bulging, you would look into the microscope, you see lots of drift on your particles as well.
Yeah, so you see here this data point in a different color, and this was even performed with a different liquid cell. We still saw a temperature increase, but going beyond that point, we even saw a bubble formation. So going to I think it was 7 electrons per square angstrom second, we even saw a kind of boiling. Yeah. So definitely drift is a thing. If you have a homogeneous distribution of particles, you probably don't care.
Yeah, true. Yeah, that's a good point. Yeah. I will do one more question. There are a couple more, but I will send them to you then via email. I will do a last question just so that we can, because we're on time. So this is also still about the temperature. The question is, how do you separate the temperature effects from beam-induced lattice conformational changes?
Beam-induced, what was the word?
Lattice conformational changes, yeah.
We did not consider this, to be honest.
Okay, well, that's fine. Well, if it's that short of an answer, I can do one more question.
I mean, what we considered is beam-induced charging. So we saw a defocus because we are using this silicon nitride based membrane. And if you heat up, you lose the focal point, what you can see here, and the diffraction rings getting more diffuse. What we did here is we added a thin layer of carbon. It just, I think it was 3 or 4 nanometers of carbon on the backside of the chip. And this already strongly reduced charging. And the second effect we took into account is window bulging, which was excluded by this highly parallel beam alignment. But yeah, sure, there might be some different effects, especially in liquid. We did these experiments in under vacuum conditions, under gaseous conditions, and under liquid conditions. Yeah.
Cool, very cool. Because we're on time and a little bit over, I'll send you, there's a couple more questions, but I'll send them to you via email so you can answer them personally. But for now, thank you so much for doing this webinar with us. It was really, well, I really enjoyed the webinar, and I hope everybody else in the attendees also did so. So for you, thank you so much, and I will put we will put the webinar also on YouTube. If there are any more questions, feel free to email us. We can always send them through to Andreas as well. And for now, have a great day, evening, or night, even if you're from the Asian region. So thank you so much, guys.
Thank you.
Have a lovely day.
Bye.
Bye.